You see my screen, right?
Yes, I can see your screen.
Okay. So yeah. So for the session today, I'm gonna just quickly go over how we can create a scalable transmission line model. And so the reason why we want to create a scalable model is that we want to quickly um, simulate the behavior of the transmission line when we sweep the length of the transmission line. For example, because in EM simulation, you sort of fix the length of the line, right? And then you EM simulate, and then you do the Wilkinson divider, for example. But then your matching is very poor. And then you have to like redo EM simulation again. You change the length or the spacing, the width or something, and then you rerun EM simulations, and then you do Wilkinson divider. And so that step is like, it's take very long to do one iterations. But with a scalable model, you can just quickly create a schematic model that you can specify the length, and then you sweep that one in simulations. And so that is the motivation for the scalable model.
So
yes.
the adjustable parameter is the length, I guess, for the transmission line.
Yeah, so you can you can have the parameters as the length, but you can also have parameter as the RLC, LG as well. So whichever parameters you want to do. So in this tutorial, I gonna set all of them parameters to be adjustable.
Oh, okay. So this is based on RLCG instead of like adjusting the width, height, or
Yeah, so this
spacing,
one
sort of.
based on RLCG.
Okay. Okay. Yep. Got it.
So this one is just a quick refreshing on the RLCG model. It basically it has you can divide it if you divide it like the transmission line into like infinitely small length, then you can model it with like L, R in series, and then G and C in shunt. And then you, if you want to capture the distributed behavior of the transmission line, then you can like do cascading with multiple RLCG models, and then you can capture the distributed behavior. And so in order to capture the RLCG, you need to do EM simulations, and then you extract the Y parameters of that EM model. Let's see. Yeah, so in here you in ADS you do a two-part simulations of the model, and then you use equations to extract the RLCG values. So in here I already provide you the equations so you can use it. I think the homework also asks you to extract the RLCG values. So yeah, so you can like do your derivations and then compare what you have with what I have and see if the derivation is correct or not. But basically it calculates gamma, which is the propagation constant, and ZT, which is the impedance of the transmission line based on Y parameters, and L, which is length of the transmission line. And then from with gamma and ZT, you can calculate G, C, R, and L based on these set of equations. And so with that, you can in ADS, you can have an option to type the equations. And so when you plot the Y parameters in ADS, you can also plot the value of these equations. And then you choose the frequency you designing at. For example, we designed 60 gigahertz. And so we choose 60 gigahertz, and then we see what the RLCG values you have. And then you save that values. So
any reason why it's the Y parameter specifically and not Z?
You can use Z. You can use people also use like ABCD parameters. For me, it's just like Y parameter is just like more intuitive for me, so I use it. But yeah, you have no limitation on any kind of parameters you can choose.
Okay.
Let's see. Yeah, so we start with like a one-piece model. So this one is like the smallest unit in the transmission line. So maybe I can pull up the model. See schematic. Yeah, so first of all, you can see there's a difference between this model and the model I showed previously. And what's the difference is that we sort of like converting from the L model. So you can see like there's an L shape here to a pi model. So with the pi model, we can make sure there's a symmetry in both input and sort of both terminals of the transmission line. And also so we have to do with this model, we cannot have sort of like we can have very low impedance path to ground, and that one can affect your DC performance. So we sort of want to decoupling the terminal to the ground, and so in here we changing from a series configuration, sorry, from parallel configuration to a series configurations, and so the DC is properly decoupled, and so in order to create a scalable model, you have to set the value of these RLCG values with it's called P par. So if you type, for example, for the resistance, if you type P par and then double quote R, and then you multiply with the length. The same thing for the length, you can also do P par length, and then once you save that, you save the schematic and create a model. Sorry, a symbol for the file. So the symbol, let's see. Yeah, so first of all, the symbol gonna look like this. It's gonna have P1, P2 for two terminals, and it has a third terminal for ground. And so let me just maybe open this one. Yeah. So if you look at the symbol of the RLCG model we just created, and to see the properties, and you can see there's a section called CDF parameters, and it has RLCG values and the length values. And so in here, we sort of like we can set the RLCG to any values we want. But in this case, I sort of create a nested parameters. So again, I still use P par C in here. So maybe we can go back to the tutorial. Yeah, so so we can create a parameterized model with the P par function, and then so this is a symbol view, and it has a CDF parameters where all of these parameters can be set to a certain values. And so with so that is one piece of the RLCG model. And so in order to create a distributed behavior, we have to do we have to cascade it like multiple of these RLCG model in series, and we can do like 5, 10, 20, 15, whatever values we want. But normally we would want to have the multiple to be more than 10. And so in here I have the model that has 10 shorter, like it's called one piece transmission line in series. And so you can see if you click on one piece and you set up the properties, and This one should be yeah. So again, like the length. This one is I set it to p power length divided by 10 because I have 10 transmission line. But if you have, like, for example, in your model you have like 15 transmission line, then you set this value to 15. And then C, G, L, and R, these are unit-wise value, so it doesn't change. So so once you have the schematic, you create a symbol. Okay, so yeah, so I can this one is a test bench, so we can open this bench. Yeah, so in here I create a test bench in Cadence to capture the behavior of the 10 pieces transmission line. And you can see, like, in the properties, we set the RLCG to proper values. So these values are the values you capture from ADS simulations. And the length is, I just set it to some parameters so I can sweep it later on. So that is that. And then maybe I can quickly run a simulations.
So the values of the C, L, R, and G, those we get from ADS, right?
Yes.
Okay.
So yeah, so these values, it's gonna depend on your layout. So it depends on your, for example, your width of the transmission line, or it can depend on the spacing of the transmission line to the ground shield.
Yep.
So, let's say make the design variable. So we can maybe start with 17 micron. And then we sweep the length at 60 gigahertz. And we can start from 50 to 150 micron. Checking this. It's too one. Okay, and then maybe we can probably applicable gain. Yeah, so you can see like we sweeping the length from 50 micron to 150 micron.
Mhm.
And we can see like S11 it's sort of changed, but it's not changed like significantly because the transmission line we're using is 50 ohms, and so it always provide good matching. But I think we should be able to see like S21 sort of decreasing a bit, and
Yeah.
the reason why we see a decreasing because the transmission line is sort of lossy. And so the longer the line, the more loss is introduced to your system.
So in this one, the length is actually the length of each unit, right? Or the whole.
So the
Oh no,
length,
sorry, you divided by the number of units. So yeah, that would be the total, I guess.
yeah. So this one is a total length.
Okay.
Yeah. So that's why in the 10 pieces schematic you see earlier, the length of each one gonna be divided by 10. Let's see. So I think that is, and then when you're done with the simulation, you should compare the results with EM simulation results and make sure what you have in here is exactly what you have in the EM simulations.
I see.
Yeah.
So a naive question would be, would the value of R be 5 ohm per unit? Just a naive guess.
So in this case, is like 5 kilo ohms.
Kilo ohms?
Yeah, because like so this one are it's gonna basically mean like the resistance per 1 meter. So this one is a unit wise value.
But these resistors are going to end up in series, right?
Yeah. So the transmission line we have is only let's say 150 micron.
Mm-hmm.
I don't have it. Yeah, but let's say it's like only in the order of like 150 micron, and so that divided by 10 gonna be 15 micron. And so if you get 50 micron, you multiply by 5.5 kilo ohms, and what you have is only like 0.08 ohm
Okay, gotcha. Per unit length.
per unit length. Yeah.
Okay.
Same thing for CGL as well. So the last thing is like so if you click on the symbol and you press Q, you can see the CDF parameters. But sometimes like this one doesn't show up. And so what we have to do is we have to go to Tools and CDF, Edit. So we're gonna choose the cell. We have the parameterized model and set the CDF layer to base. Basically, this if we set it to base, then it's gonna store permanently to your drive. And then make sure like all of the values are listed in here. The type is string, and if you click on one value on C value, for example, then make sure the parse as CEL set to yes, and parse as number set to yes. So once you do that, then you can go back to your schematic and you can see the CDF parameters.
Okay.
Yeah. I think that is it for the tutorial. The tutorial I posted online gonna be pretty descriptive, so I think it's easy to follow.
Okay. Thank you. I think that was good.
Yeah. Stop this.